Pluto is a distant and confusing smaller planet that was once an individual member of our planetary system's family. However, late astonishing statements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggested that this cool world is on an expected collision course with Neptune. Yet how could this occur, and what may be the consequences of such a gigantic event? Are we seeing an unexpected infinite peculiarity, or is there something else to this approaching divine crash? Join us as we investigate the possible results of a Pluto-Neptune influence. Pluto, a previous planet that was downsized to a dwarf planet, remains a subject of interest and study in the cosmic community. As indicated by later forecasts from leading scientists, Pluto's orbit is dangerously near Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially risky impact between these two planets, which could represent a critical risk to Earth. But how is such an event even conceivable? Pluto's excursion around the Sun is unlike any other planet in our solar system. It requires a stunning 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution. Yet the interest doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, wandering significantly from the near-round orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, determined at 17 degrees to the ecliptic plane. The way Pluto follows its orbit is considerably more extreme compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating parts of Pluto's orbit is its crossing point with Neptune's orbit. For around 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, resisting what we might expect based on their positions in the planetary system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The investigation of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its unusual path. Unlike other planets whose orbits lie mostly near the ecliptic plane, Pluto's orbit protrudes with its steep inclination and stretched shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricate mechanics of space. The three-body problem in space involves figuring out how three objects like Pluto, Neptune, and the Sun move and interact with each other due to their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. The terms alpha libration and degree libration, along with the VZK oscillation, are key to solving this puzzle, as indicated by astrophysicists. What keeps all planets in their orbits is a phenomenon called alpha libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is found no less than 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from crossing. Extension libration, on the other hand, refers to the upward movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned completely above their orbital plane, offering an additional layer of protection from potential impacts. Another important factor in this situation is the VZK oscillation, named after three scientists, Bon Zippel, Leo, and Kai, who studied how objects move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational pull influences how they move. In Pluto's case, the VZK helps explain why its orbit around the Sun is so unusual despite its seemingly erratic path. This oscillation helps keep Pluto moving smoothly for billions of years. The VZK oscillation shows that even though things in space may seem turbulent and random, some patterns and forces keep everything together. These factors help maintain Pluto's orbit, ensuring it doesn't crash into Neptune or lose its way. This three-body problem is fundamental for understanding how orbits change because of how space objects pull on each other. Studying this helps us learn more about Pluto, our solar system, and distant stars and galaxies. Mathematical simulations in the late 1980s revealed that despite these stabilizing properties, Pluto's orbit is actually chaotic, with slight deviations in initial conditions leading to massive changes over time. However, these unusual properties of Pluto's orbit have been found to maintain stability over very long time scales, effectively keeping the chaos in check. Recent computer models have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a special relationship with Pluto where for every 2 orbits Pluto completes around the Sun, Neptune finishes 3. This resonance helps stabilize Pluto's orbit. But Neptune isn't the only factor. Jupiter's gravity also plays a huge role in shielding Pluto's orbit, and Saturn contributes as well. These studies show that Jupiter's gravity alone is powerful enough to ensure Pluto stays on a stable path for a long period of time, possibly even billions of years. So it's like Neptune, Jupiter, and Saturn are working together to make sure Pluto keeps moving safely in space without getting into trouble. These peculiarities are essential in the larger context of the universe, keeping everything in order and maintaining stability in the movement of celestial bodies. Without these mechanisms, the solar system as we know it would be a much more chaotic place, with bodies like Pluto possibly crashing into others or being ejected from their stable orbits, leading to a cascading effect on other celestial objects. For Pluto, especially in discussions about its potential collision with Neptune in the future, understanding its orbit is crucial. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto shows how even the most seemingly unstable orbits can reach a state of equilibrium through the intricate interaction of gravitational forces and orbital mechanics. It also highlights the importance of ongoing observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the bizarre nature of celestial bodies, and Pluto's orbit is a perfect example of this phenomenon. The concept of orbital chaos, which refers to the sensitive dependence of a body's path on its initial conditions, is clearly illustrated in the case of Pluto. This means that even slight changes in Pluto's position or speed can significantly alter its long-term course within the vast expanse of our solar system. Pluto occupies a unique position that challenges how we understand planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant discoveries about its composition and behavior. One of the most interesting aspects of Pluto is its surface, which is a complex tapestry of ice, rock, and other compounds. The New Horizons mission, which flew by Pluto in July 2015, provided incredible data about this distant world. Pluto's surface is characterized by vast plains, towering mountains, and deep valleys. One of the most striking features is Sputnik Planitia, a massive heart-shaped plain primarily made of nitrogen ice. This region showcases a diverse array of geological features, including massive ice blocks and what appear to be flowing glaciers. The presence of these features suggests that Pluto might still be geologically active despite its great distance from the Sun and low temperatures. Another intriguing aspect of Pluto is its atmosphere, primarily composed of nitrogen with traces of methane and carbon monoxide. Pluto's atmosphere is thin but exhibits fascinating seasonal variations. As Pluto moves closer to the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior reflects the complex interaction between Pluto and its environment. During Pluto's closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies orbit a point in space that lies between them, rather than Pluto simply orbiting Charon. This unique relationship adds to the gravitational dynamics of the region, affecting the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated by small icy bodies, is home to many other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, offering scientists a glimpse into its formation. Pluto's orbital characteristics may provide insights into the migration patterns of these distant objects, suggesting that interactions with larger planets may have played a key role in shaping their current orbits. One of the key implications of understanding Pluto's orbital dynamics is its potential impact on our understanding of the solar system's evolution. The gravitational influences from nearby giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including those in the Kuiper Belt. Such interactions can lead to changes in orbits, potentially causing collisions or ejection from the solar system. As scientists continue to study these interactions, they may uncover broader patterns that govern the behavior of celestial bodies across the universe.